Hi there everyone, welcome to the first lesson on compound angles. In this lesson, we want to look at the proofs of the following compound and double angle expansions. The cos of A minus B, the cos of A plus B, the sine of A minus B, the sine of A plus B, the cos of 2A, and the sine of 2A. Then we also want to look at some typical theory questions on compound angles. The first compound angle expansion says that the cos of A minus B equals the cos of A times the cos of B plus the sine of A times the sine of B. So let's look at the proof of the cos expansion for A minus B. We start by drawing a unit circle, in other words a circle of radius 1. Now we draw a line segment from the center of the circle to a point P on the circumference. The length of OP is 1 unit, since it's a radius of the circle, and we're dealing with a unit circle. We also let the angle that OP makes anticlockwise with the positive x-axis be equal to A. Now we drop a perpendicular from point P onto the positive x-axis, and we can call this PR. Inside triangle POR, OR over OP is the cos of angle A. But since OP is equal to 1 unit, we find that OR is the cos of A. Of course, OR is the x-coordinate at point P. So then the x-coordinate at P equals the cos of A. Also inside triangle POR, PR over OP is a sine of angle A. And once again, since OP is equal to 1 unit, we find that PR is a sine of A. Of course, PR is the y-coordinate at point P. So then we find that the y-coordinate at P is a sine of A. We now construct a second line segment from the center of the circle to a point Q on the circumference. Of course, OQ is also equal to 1 unit, since it's another radius of the unit circle. We also let the angle that OQ makes with the positive x-axis anticlockwise equal B. Now we drop a perpendicular from point Q onto the positive x-axis, and we can call this QS. Inside triangle QOS, OS over OQ is the cos of angle B, but since OQ is equal to 1 unit, we find that OS equals the cos of B. Of course, OS is the x-coordinate at point Q, so then the x-coordinate at Q equals the cos of B. Then also inside triangle QOS, QS over OQ is a sine of angle B. But once again, since OQ is equal to 1 unit, we find that QS is a sine of B. QS, of course, is the y-coordinate at point Q. So then the y-coordinate at Q equals a sine of B. Now that we have the coordinates of points P and Q respectively, we connect them with a line segment PQ. And we're going to use the distance formula to find PQ squared. Recall that the distance formula says that if we have 2 points on the line, x1, y1 and x2, y2 respectively, then the distance squared between them will be x2 minus x1 all squared plus y2 minus y1 all squared. So we can let the coordinates at P and Q be x1, y1 and x2, y2 respectively, and then use the distance formula to find PQ squared. So then PQ squared will equal x2 minus x1 all squared plus y2 minus y1 all squared. We can square out both sets of brackets. So it's going to be cos squared b minus twice the cos of a times the cos of b plus the cos squared of a. And in squaring out this set of brackets, it's going to be plus the sine squared of b minus twice the sine of a times the sine of b and plus the sine squared of a. Now the cos squared of b plus the sine squared of b, that gives us 1 by the squares identity, and the cos squared of a plus the sine squared of a also gives us 1. And of course we're still left with these two terms. Of course, we can add the 1's, and this is what we're left with. Before we continue with the rest of the proof, you should note that inside triangle POQ, angle POQ is equal to A minus B. We now want to set up a second equation for PQ squared, but this time using the cosine rule. Recall that the cosine rule says, in triangle ABC with sides small a, small b, and small c respectively, a squared is equal to b squared plus c squared minus twice bc times the cos of a. So let's use the cosine rule to find another equation for PQ squared. So then PQ squared, using the cosine rule, will equal OP squared plus OQ squared minus twice OP times OQ times the cos of the included angle here. In other words, times the cos of A minus B. We can fill in the values of OP and OQ, and of course they are 1 each. So it's going to be 1 squared plus 1 squared minus twice 1 times 1 times the cos of A minus B. And we can simplify this to 2 minus twice the cos of A minus B. So we now have a second equation for PQ squared. So these are the two equations we have for PQ squared. One is from the distance formula and one from the cosine rule. Since both the right-hand sides of these equations are equal to PQ squared, we can make them equal to each other. So then 2 minus twice the cos of A minus B will equal the right-hand side of this equation. So 2 minus twice the cos of A times the cos of B minus twice the sine of A times the sine of B. We can simplify this equation. The 2's will cancel on both sides. And then we can divide through by negative 2. So divide through by negative 2. Then on the left-hand side, we're going to be left with the cos of A minus B. On the right-hand side, the negative 2 will cancel out here, as well as over here. And we're left with the cos of A times the cos of B plus a minus divided by a minus is a plus. So the cos of A times the cos of B plus a sine of A times the sine of B. And this completes the proof. The second compound angle expansion says that the cos of A plus B equals the cos of A times the cos of B minus the sine of A times the sine of b. Before we can look at the proof of this theorem, in other words, the proof of the second compound expansion, we need to briefly revisit negative angles from previous levels of study. We know that a negative angle is measured clockwise from the positive x-axis on the cast diagram. So the angle negative theta lies in the fourth quadrant, theta being numerically less than 90. So the sine of negative theta is negative the sine of theta, because sine is negative in the fourth quadrant. The tan of negative theta is equal to negative the tan of theta for the same reason, but the cos of negative theta equals the cos of theta, because cos is positive in the fourth quadrant. We use the first compound angle expansion, in other words that for cos of a minus b, to prove the second one with. So this is what a question would generally look like in the exam. It says, given the cos expansion for a minus b, prove the cos expansion for a plus b. So we can start with the left-hand side of what we need to prove. It's of course cos of a plus b. Now we rewrite the a plus b as a minus negative b. So a minus negative b. And now we can use the expansion for cos of a minus b. And wherever we have a b, we're going to put in negative b. So it's a cos of a times the cos of negative b now, then plus the sine of a times the sine of negative b. And as we saw, the cos of negative theta is the cos of theta, but the sine of negative theta is negative the sine of theta. So we're going to write cos a, and here we're going to have cos b. Then the sine of negative b becomes negative the sine of b, and we can put the negative sign in front here. So minus sine a times sine b. Then the third compound angle expansion says that the sine of a plus b equals the sine of a times the cos of b plus the cos of a times the sine of b. So this is typically how the sine expansion for a plus b is asked in the exam. We are given the cos expansion for a minus b, and we have to use it to prove the sine expansion with. So we can start with the left-hand side of what we need to prove. The left-hand side here, of course, is a sine of a plus b. So the sine of a plus b. And we're going to use co-ratios. Recall that the cos of 90 degrees minus theta is a sine of theta. So we're going to rewrite the sine of a plus b as the cos of 90 degrees minus a plus b. In this case, a plus b takes the place of theta. So the cos of 90 degrees minus theta is a sine of theta. And now we're going to simplify a little bit, or manipulate a little bit. We're going to multiply the negative into the round brackets over here. And we're going to group the first two terms together over here. So we have the cos of 90 degrees minus a minus b. Now, if you compare what we have over here with the cos expansion for a minus b, here we have 90 degrees minus a, which we can regard as one angle, minus b. and here we have a minus b. So the 90 degrees minus a basically takes the place of a in this expansion. So we're going to apply this expansion, but wherever we have an a, we're going to put in 90 degrees minus a. So it's going to be the cos of a, but now we write 90 degrees minus a times the cos of b. Then plus the sine of a, but once again we're going to write the sine of 90 degrees minus a then times the sine of b. Now we're going to use the co-ratios again. We know that the cos of 90 degrees minus theta is a sine of theta. So the cos of 90 degrees minus a is a sine of a. And the sine of 90 degrees minus a is the cos of a. So we see here that the left-hand side, which is this over here, comes to the right-hand side. And we have proved this identity. Then, coming to the fourth compound angle expansion, it says that the sine of a minus b equals the sine of a times the cos of b minus the cos of a times the sine of b. So this is how the proof of this theorem is asked in the exam. We are given the sine of a plus b, or the expansion thereof, and we have to use it to prove the sine of a minus b. So let's start with the left-hand side of what we need to prove. So the left-hand side is the sine of a minus b. And we basically rewrite a minus b as a plus negative b. Now we use the expansion for sine of a plus b, but instead of b, we're going to write negative b. So it's a sine of a times the cos now of negative b plus the cos of a times the sine of negative b. We know that the cos of negative b is positive the cos of b. So we have the sine of a times the cos of b. We also know that the sine of negative b is minus the sine of b. So plus the cos of a times negative sine of b. Now we can rewrite everything on the right hand side here. So a plus times a minus is a minus. So we have the sine of a times the cos of b minus the cos of a times the sine of b. And this completes the proof. Then coming to the fifth compound angle expansion, it says that the cos of 2a can be equal to any one of the following three expressions. It can be equal to the cos squared of a less the sine squared of a. It's also equal to twice cos squared a minus 1. And it's also equal to 1 minus twice the sine squared of a. These three expansions of cos 2a are known as double angle expansions, since 2a is considered to be a double angle. Let's look at the proof for the expansion, or for each of the three expansions for cos 2a. The first one says that the cos of 2a equals the cos squared of a less the sine squared of a. So let's look at the proof of this. We're going to use the expansion for cos A plus B. We know that this is equal to cos A times cos B minus sin A times sin B. Now we're going to look at the left-hand side here. So the left-hand side of what we need to prove, it's a cos of 2A. And this, of course, we can write as the cos of A plus A. So the cos of A plus A. Then, using the expansion for cos A plus B, we can replace each B with an A. So it's going to be the cos of A times the cos of A less the sine of A times the sine of A. And this, of course, is equal to cos squared A. So cos A times cos A gives us cos squared A less sine squared A. So we see that the left-hand side, in other words, cos 2A, comes to the right-hand side. And hence we have proved this theorem. Then, in a second double expansion or double angle expansion for cos 2A, we have to prove that the cos of 2A equals twice the cos squared of A less 1. This is relatively straightforward to prove because we already know that the cos of 2A is equal to the cos squared of A less the sine squared of A. We want to write the right-hand side of this equation entirely in terms of cos. So we use squares identities. So it's a cos squared of A less, and we know that according to the squares identity, the sine squared of A is 1 less the cos squared of A. Now we simplify and add like terms. So it's a cos squared of A, and we can multiply the minus into the brackets. And then, of course, cos squared A plus cos squared A is twice cos squared A. And we have the desired result. Then coming to the proof of the third and last double angle expansion for cos 2A, we have to show that cos 2A is 1 minus twice the sine squared of A. Now, we already know that the cos of 2A is equal to the cos squared of A minus the sine squared of A. We want to write the right-hand side here entirely in terms of sine. And once again, we use the squares identity. We know that cos squared A is equal to 1 minus sine squared A. Now we simply add like terms. Minus sine squared A minus sine squared A, of course, is minus twice sine squared A. And this comes to the right-hand side of what we needed to prove. The last two expansions for cos 2A lead to two very useful equations. Let's look at the first one. We saw that the cos of 2A is equal to twice the cos squared of A minus 1. Let's see what happens when we make cos of A the subject of the formula. So we have the cos of 2A equal to twice the cos squared of A less 1. We can take the negative 1 to the left-hand side, and then we'll get twice the cos squared of A equals the cos of 2A plus 1. Now we can divide the 2 into the right-hand side, and we get that the cos squared of A equals the cos of 2A plus 1 all over 2. Now we simply take the square root on the right-hand side. So we end up with the cos of A being equal to plus or minus the square root of the cos of 2A plus 1 all over 2. So this is the one equation that's very, very useful that we can get out of this one. Then secondly, we also saw that the cos of 2a can be written as 1 minus twice the sine squared of a. In this case, we want to make sine a the subject of the formula. So we can bring the negative 2 sine squared a to the left-hand side. So it's 2 sine squared of a. And we can take the cos of 2a to the right-hand side. So it's 1 minus the cos of 2a. Now we can divide by 2 on the right-hand side. So it's 1 minus the cos of 2a all over 2. And then finally, we can take the square root on the right-hand side. So we see that the sine of a can also be written as plus or minus the square root of 1 minus cos 2a, all divided by 2. So this is the second useful equation that we can get out of the cos 2a expansion. And we're going to use it later on. The first theory question here deals with proving the cos expansion for theta minus beta. It's the same method that we used to prove the cos expansion for a minus b right at the beginning of this lesson, except that we have different letters and the sketch is slightly different. So you should try and do this proof on your own first before you look at the solution. But before you do that, make sure that you've studied the proof we did right at the beginning of the lesson very thoroughly. So in this question, we are told that points P and Q lie on the circle of radius 2 units with center at the origin. And we have to use the sketch to prove the cos expansion for theta minus beta. So let's have a look at it. I've redrawn the sketch over here. Now, important to note that beta is the angle that OQ makes anticlockwise with the positive x-axis, and theta is the angle that OP makes anticlockwise with the positive x-axis. We need to prove the cos expansion for theta minus beta. And just like in the standard proof that we looked at right at the beginning, we have to put the coordinates of Q and P in terms of beta and theta respectively. So let's start with beta, and we want to write the coordinates of Q in terms of this angle, beta. So we're going to work inside this triangle over here. So triangle OQK. So inside this triangle. Of course, this is a right angled triangle. So we want to work inside triangle OQK. Now, important to note that we are interested in the coordinates at Q. And OK gives the x coordinate at Q, while QK gives the y coordinate at Q. So OK over OQ will be the adjacent over the hypotenuse. And of course, that's the cos of beta. But also note that we were told the radii of the circle, or radius of the circle, comes to 2 units. So these are both 2 units, OQ and OP. So we can replace OQ here with 2 units. So then OK over 2 units will give the cos of beta. And hence OK is 2 times the cos of beta. And we said that OK is the x-coordinate at Q. So then the x-coordinate at Q will be 2 cos beta. We now have to find the y coordinate, and we said that's given by qk. So let's find the y coordinate. So then, also inside triangle OQK, OK, or rather QK, so QK over OQ will be the opposite over the hypotenuse, and that's of course the sine of beta. But once again, OQ is a radius, which is 2 units. So QK over 2 units equals the sine of beta. And then we can find QK is going to be twice the sine of beta. But we said that QK is the y coordinate at Q, at this point Q. So then the y coordinate at Q will be 2 times the sine of beta. So now that we have the coordinates at Q, we can continue to find the coordinates at P. So let's do that. So in this case, we're going to work inside triangle OLP. So inside this triangle here, so triangle OLP. And we're going to write the coordinates of P in terms of theta. So we're working inside, so in triangle OLP. Also note that OL here will be the x coordinate at point P, and LP will be the y coordinate at point P. So let's start with OL. We know that OL, so OL over OP. So it's going to be the adjacent side to angle theta, OL, and OP of course is the hypotenuse. So OL over OP will be the cos of theta. Once again, OP is a radius, so it's 2 units. So we know that OL over 2 equals the cos of theta, and hence OL is twice the cos of theta. But we said that OL is the x-coordinate at P. So then the x-coordinate here will be 2 cos theta. Let's find the y-coordinate. We said the y-coordinate at P is given by LP. So then LP, which is the opposite side to angle theta, the opposite to theta, LP over OP. And OP, of course, is the radius. So we have the opposite over the hypotenuse. We know that this is going to be the sine of theta. And OP is 2 units, so we can write that LP over 2 is a sine of theta. And hence LP equals twice the sine of theta. And of course we said LP is the y-coordinate at point P. So the y-coordinate then is twice the sine of theta. Now that we have the coordinates of P and Q respectively, we're going to use the distance formula to find PQ squared here. So if we let the coordinates of Q, for example, be x1 and y1 respectively, and those at P be x2 and y2 respectively, then using the distance formula, and we know that the distance formula says the distance squared is the difference between x2 and x1 all squared plus the difference between y1 or y2 rather, and y1 all squared. So then applying the distance formula here for pq squared, we're going to have pq squared equals, so x2 minus x1 will be 2 cos theta minus 2 cos beta. So it's going to be 2 cos theta minus 2 cos beta all squared plus the difference in the y's. So y2 minus y1 will be 2 sine theta minus 2 sine beta. So 2 sine theta minus 2 sine beta all squared. We're going to square out on the right hand side here. So we're going to use this basic rule of algebra. We know that a plus b all squared is a squared, so the first term squared, plus the first term times the second term times 2, so twice ab, plus the second term squared. So then applying it here, it's going to be the first term squared, which is 4 cos squared theta, then this sign, then the first term times the second term times 2. So 2 cos theta times 2 cos beta is 4 cos theta cos beta times 2 is 8 cos theta cos beta. And then plus the second term squared. So plus 4 cos squared beta. Then we square out here as well similarly. So the first term squared will be 4 sine squared theta. Then it's a first term times a second term times 2. So it's minus, and we're going to get 8 sine theta sine beta. And then of course the second term squared here will give 4 sine squared beta. Let's simplify this. So if you look at this, 4 cos squared theta plus 4 sine squared theta. Let's see what that gives us. 4 cos squared theta plus 4 sine squared theta. We can write as 4 into cos squared theta plus sine squared theta. So we're basically taking out a common factor between these two terms. Then, if you look at 4 cos squared beta plus 4 sine squared beta, once again we can take out 4 as a common factor. So it's 4 into cos squared beta plus sine squared beta. Then of course we are still left with these two terms. So we're left with these two terms. So let's rewrite them. So it's negative 8 cos theta cos beta, then minus 8 sine theta sine beta. Now we have the squares identity over here. Cos squared theta plus sine squared theta is 1. So it's basically 4 times 1, or just 4. And the same over here. Cos squared beta plus sine squared beta is 1. So it's just plus 4 over here as well. And then of course we have negative 8 cos theta times cos beta minus 8 sine theta sine beta. And now we can add the 4's to get an 8 here. So we now have an equation for PQ squared, which is this over here. And we got this by using the distance formula. We're now going to set up a second equation for PQ squared. But this time we're going to use the cosine rule. So I've duplicated the sketch again over here. Now, just recall that the cosine rule works as follows. So if I have triangle ABC with sides C, B, and A respectively, then A squared is going to be B squared plus C squared minus twice BC times the cos of angle A. In other words, twice BC times the cos of the included angle between B and C. So between these two sides. This time we're going to use triangle OQP and use the cosine rule inside here. Now, before we can do this, just notice that this angle here is theta, measured anticlockwise from the positive x-axis. So this angle is theta. Then this angle here is beta. Then angle O, or rather angle QOP. So this angle here is going to be theta minus beta. So theta minus beta. So it's theta less beta. So then working inside this triangle, inside triangle QOP, and applying the cosine rule, we can see that QP, or PQ squared rather, is going to be OQ squared. OQ squared plus OP squared minus twice OQ times OP times the cos of angle QOP. In other words, the cos of theta minus beta. So theta minus beta. So then we can write PQ squared as, of course, we said earlier that OQ is a radius, and so is OP. They're both equal to 2 units. So we can replace OQ and OP with 2 units. So 2 squared plus 2 squared minus twice OQ, in other words 2, times OP, 2 times the cos of theta minus beta. So we have 4 plus 4, which is 8. 2 times 2 times 2 is 8. And then cos theta minus beta. So you can see that we now have a second equation for PQ squared. And this time we got it from using the cosine rule inside this green triangle here, inside triangle QOP. So this is the second equation then. So as we said, the first equation here comes from using the distance formula. That is the equation for PQ squared. And the second one here came from the cosine rule. We're now going to combine the two equations. So this here must come to this. They're essentially the same thing. Right, now we can see that when we simplify, the 8's cancel on both sides. And then we can divide through by -8, which appears in all these terms that remain. So we're going to divide through by -8. So then on the left-hand side here, we're left with cos theta minus beta. On the right-hand side, the -8's cancel out here. So we're left with cos theta cos beta. Then we know that a minus divided by minus is a plus. So then plus sine theta sine beta. And this then completes the proof. So then we can say, therefore, the left-hand side equals the right-hand side of what we needed to prove originally, which is this over here. So in A here of question 2, we have to use the cos expansion for alpha plus beta to derive the formula for sine of alpha minus beta width. This, of course, is a standard derivation which you need to learn. So let's have a look at it. We want to derive the expansion for sine of alpha minus beta. Now, we're going to use a co-ratio. We know that the sine of theta is equal to the cos of 90 degrees minus theta. So then applying this co-ratio here, we don't have theta. We have alpha minus beta. So we're going to replace theta in this equation with alpha minus beta. So the sine of alpha minus beta is the same as the cos of 90 degrees, not minus theta, but minus alpha minus beta. So this is the same as saying the sine of theta equals the cos of 90 degrees minus theta. Now we're going to manipulate slightly inside the square brackets here. So we're going to multiply the negative into the round brackets. Then a minus times a minus is a plus. And now we're going to regroup inside the square brackets. We're going to group the first two terms together. So we have that the sine of alpha minus beta is equal to the cos of 90 degrees minus alpha plus beta. Now let's compare this with what we were given. We were given the cos expansion for alpha plus beta. So let's just copy this. So we don't have the cos of alpha plus beta. We have the cos of 90 degrees minus alpha plus beta. So instead of an alpha here, we have 90 degrees minus alpha. So then applying this expansion to what we have on the right-hand side here, we merely have to replace alpha here with 90 degrees minus alpha. So it's a cos of alpha, but now of course the cos of 90 degrees minus alpha times the cos of beta, then minus the sine of alpha, which now is the sine of 90 degrees minus alpha, and then times the sine of beta. Then using co-ratios again, we know that the cos of 90 degrees minus alpha is a sine of alpha, and the sine of 90 degrees minus alpha is a cos of alpha. So now we have derived an expansion for the sine of alpha minus beta by using the cos expansion for alpha plus beta. Then in B, we have to use the cos expansion for a minus b to derive the formula for sine of a minus b width. So it's very similar to the first derivation. So let's start with the sine of a minus b. Once again, we're going to use co-ratios. So I'm going to write the sine of a minus b as the cos of 90 degrees minus a minus b. And we're going to simplify inside the square brackets again. So we're going to multiply the negative into the square brackets. So we get the cos of 90 degrees minus A plus B. Now, remember that we now have to use the expansion for cos of A minus B. So we need to get this in the required form. So once again, we can group inside the square brackets. But we're going to take an additional step here. We're going to write the plus B as minus negative B. So now we have this in the form A minus B. Instead of A, though, we have 90 degrees minus A. So if we compare this with the cos expansion for A minus B, and let's copy this again. As we said, instead of A, we have 90 degrees minus A. And instead of B, we have negative B. So if you apply this expansion, we have to replace each A in this equation with 90 degrees minus A and each B with negative B. So let's do that. So it's a cos of A, in other words, the cos of 90 degrees minus A now, times the cos of B. In this case, it will be the cos of negative B. Then plus the sine of A, which is now the sine of 90 degrees minus A, times the sine of B. In other words, the sine of negative B. So once again, we're using this expansion, but wherever we have an A, we put in 90 degrees minus A, and wherever we have a B, we put in negative B. Then applying co-ratios here again, the cos of 90 degrees minus A is a sine of A. Then the cos of negative B. Recall that negative B is an angle in the fourth quadrant. A negative angle is measured clockwise from the positive x-axis. So the cos of negative B is a cos of an angle in the fourth quadrant. And we know that cos is positive in the fourth quadrant. So the cos of negative B is simply the cos of B. Then the sine of 90 degrees minus A is, of course, the cos of A using co-ratios. The sine of negative B is a sine of an angle in the fourth quadrant. We know that sine is negative in the fourth quadrant. So then the sine of negative B is minus the sine of B. So here we have the cos of A times a negative sine of B. A plus times a minus is a minus. So we end up with the cos of A minus the cos of A times the sine of B. And we have now derived an equation for the expansion for sine of A minus B by using the cos expansion for A minus B. Then coming to C, here we have to use the cos expansion for A minus B to derive the formula for sine of A plus B with. And we're going to do it in a very similar way to A and B. So it's a sine of A plus B. Then using co-ratios again, we can write this as the cos of 90 degrees minus A plus B. In other words, the sine of theta is the cos of 90 degrees minus theta. Once again, we're going to multiply the minus into these round brackets. And we're going to regroup. We're going to group the first two terms together. And this is in the form cos of A minus B, which is what we need to use. Except for having an A, we have 90 degrees minus A. So we can apply this expansion and just replace A with 90 degrees minus A. So it's going to be the cos of A. So the cos of 90 degrees minus A times the cos of B. Then plus the sine of A, but now it's a sine of 90 degrees minus A times the sine of B. Then using co-ratios again, the cos of 90 degrees minus A is a sine of A, and the sine of 90 degrees minus A is the cos of A. And here's the derivation then for the sine expansion for A plus B by using the cos expansion for A minus B. So in D, we have to prove that the sine of A plus B minus the sine of A minus B equals twice the cos of A times the sine of B. So let's start with the left-hand side. It's a sine of A plus B minus a sine of A minus B. Now, we know the sine expansion for A plus B. So the sine of A plus B, so this term here, we know that this is equal to the sine of A times the cos of B plus the cos of A times the sine of B. So we can replace the sine of A plus B with this expansion. So it's a sine of A times the cos of B plus the cos of A times the sine of B. Then we have minus the sine of A minus B. And we know that the sine of A minus B is a sine of A times the cos of B minus the cos of A times the sine of B. So we can replace the sine of A minus B with sine A times cos B minus cos A times sine B. We're going to put it in brackets because this minus here will affect what's inside the brackets, or will affect this expansion. So then the sine of A minus B is the sine of A times the cos of B minus the cos of A times the sine of B. We're going to multiply this negative into the brackets here. Then a minus times a minus is a plus. Now, if you look carefully at this that we have here, we can see that the sine of A times the cos of B will cancel here with the sine of A times the cos of B. So these two terms cancel. And we're basically left with cos A sine B plus cos A sine B, which of course is twice cos A sine B. And this is equal to the right-hand side of this identity that we needed to prove. So this equals the right-hand side. And hence we can say the left-hand side equals the right-hand side.